Our universe was born in a fireball we call the Big Bang, but in the very first sliver of a second, something far stranger happened. A brief, explosive growth spurt known as cosmic inflation stretched the fabric of space itself faster than light. In less time than it takes to blink, a subatomic speck was blown up to become our entire observable cosmos. This fleeting era set the stage for every galaxy, star, and planet we see today. Yet it remains one of the greatest enigmas in all of science. By the end of this journey, you will understand 25 of the most profound mysteries left behind by this cosmic dawn. How could a quantum whisper create the vast cosmic web? And what if our entire universe is just one bubble in an infinite, bubbling multiverse? What single question about our cosmic beginning keeps you wondering late at night? That first unimaginable moment holds the ultimate question. What, or perhaps who, lit the fuse for the Big Bang itself? Before the frantic expansion of inflation even began, there must have been a trigger, a catalyst that set everything into motion from a state we can scarcely describe. Physicists call this the problem of the initial singularity, a point of infinite density and temperature where the known rules of the universe simply cease to apply. Our mathematics breaks down, our physics melts away, leaving us staring into a profound abyss of ignorance. One compelling idea suggests that our entire cosmos could have sparked into existence from a random quantum fluctuation, a tiny ripple in the fabric of nothingness that, against all odds, blossomed into everything we see. Think of it like a cosmic free lunch, where the positive energy of all the stars and galaxies is perfectly balanced by the negative pull of gravity, allowing for a universe to pop into being from nothing at all. Another, even more mind-bending proposal from string theory involves a collision between vast, multidimensional membranes, or brains for short, shaking a dormant realm into a fiery birth. Yet for all these brilliant ideas, the truth is that the trigger remains entirely hidden from us. The ferocious energy of the subsequent inflationary period effectively erased any evidence of what came before, like a cosmic wildfire scorching away all traces of what originally grew in the soil. So we are left with this fundamental mystery, the question of all questions. What was the first cause? What existed before existence? The search for that answer continues to drive us forward, pushing the very boundaries of human understanding. This mysterious trigger, whatever it was, unleashed an even greater cosmic actor, a force so potent it sculpted the infant universe. This is the inflaton field, the invisible engine of cosmic inflation. Think of it not as a substance you can touch, but as an all-pervasive energy field, a kind of cosmic hum filling the emptiness of space. Its unique property was a state known as a false vacuum, a condition of unstable high energy. This false vacuum energy had a bizarre and counterintuitive effect. It generated a powerful repulsive gravity. Instead of pulling things together, this gravity pushed space itself apart, and it did so with unimaginable ferocity. The universe did not just expand, it swelled exponentially, doubling in size over and over again in fractions of a second. This is the inflaton field's greatest legacy, the reason our cosmos is so vast and uniform. But what was this field really? We have never directly detected it. Our best clues come from its cousins in the quantum world, like the famous Higgs field that gives particles their mass. The inflaton field is thought to be a similar kind of entity, a fundamental part of reality's fabric, but one that operated at energy levels far beyond anything we can recreate. The search for its echoes is a primary goal of modern cosmology, hidden in the faint patterns of the cosmic microwave background, the ancient light from the Big Bang. Finding proof of the inflaton would not just solve one mystery, it would open a direct window into the highest energies and most fleeting moments of creation, revealing the identity of the very architect that built our cosmic home. But that incredible engine of expansion could not run forever. Its sudden stop is just as vital and just as mysterious as its start. This is the graceful exit problem, the puzzle of how the furious growth of inflation came to a smooth and timely end. For our universe to become the structured cosmos we know, the inflaton field had to shut itself off. The leading theory describes this as a roll down a hill. Picture the field not as a static force, but as a ball perched at the very top of a steep energy slope. This high point represents the false vacuum, that unstable state driving the hyper-expansion. For inflation to end, the ball simply needed to roll down into the valley below, a state of lower, stable energy. As it rolled, the field would have wobbled, and those wobbles are thought to have been the very source of all matter and energy, a process called reheating. The universe, cold and empty from its rapid stretching, was suddenly flooded with a hot soup of particles, the raw material for everything to come. Yet this simple analogy hides a deep complexity. What was the exact shape of that hill? A gentle slope would have ended inflation too slowly, potentially creating a universe far less uniform than our own. A steep cliff with a bumpy bottom could have made the ball oscillate wildly, creating violent, uneven pockets of density. The transition had to be just right, a graceful exit that perfectly set the stage for the next act, the hot Big Bang. The unknown details of this single event determine the entire initial condition of our universe. Without a smooth and complete reheating, the cosmic story might have ended right there with a cold, empty, and forever expanding void. This graceful exit from inflation might not have been universal. What if, in some regions of space, the inflaton field never rolled down that hill? The theory of eternal inflation proposes exactly that, suggesting our entire cosmos is just one bubble in an infinite, frothing ocean of reality. Picture the end of inflation not as a single event, but as a patchwork process. In most areas, the field lost its energy and settled down, creating a stable pocket like our own universe. But thanks to random quantum jitters, in other regions the field could have been kicked back up the energy slope. In those spots, the hyper-expansion would have reignited, stretching space even more ferociously. This process could repeat endlessly, with each new inflationary region eventually cooling into its own separate bubble universe, forever disconnected from our own. The staggering implication is a multiverse, a cosmic landscape where the fundamental constants of nature are set by random chance. In one bubble, gravity might be strong, instantly crushing any possibility of stars. In another, the forces that hold atoms together could be too weak, preventing matter from ever forming. Our universe, with its just right conditions for life, would be a single lucky ticket in an infinite cosmic lottery. This idea pushes the limits of science itself. How can we ever test for the existence of other universes if they are forever beyond our observational horizon? The concept remains a profound and controversial frontier, a theory that could explain the bizarre fine-tuning we see around us, or one that might forever reside in the realm of untestable philosophy. It forces us to ask, is our universe a unique, special creation, or merely one average member of an infinite cosmic ensemble? While the multiverse remains a tantalizing possibility, the search for definitive proof of inflation brings us back to a specific, ghostly signal imprinted on the sky. This is the hunt for primordial gravitational waves, ripples in the very fabric of space-time created during that explosive growth spurt. Think of the infant universe not as a smooth, placid pond, but as a turbulent sea, churned by the immense energies of the inflaton field. These quantum jitters, stretched to cosmic proportions by inflation, would have created undulations in space-time itself, gravitational waves that have been traveling through the cosmos ever since. Detecting them would be the ultimate smoking gun, direct evidence from the first moments of existence. The challenge is that these waves are incredibly faint, but cosmologists have a brilliant strategy for finding them. They look for the unique fingerprint these waves left on the oldest light we can see, the cosmic microwave background. As this ancient light traveled for billions of years, the stretching and squeezing of space-time from gravitational waves would have subtly twisted its polarization, creating a distinctive swirling pattern known as B-modes. Finding this specific pattern in the CMB is like finding the signature of the inflaton field itself. Projects like the BICEP telescope at the South Pole have spent years staring at a pristine patch of sky, searching for this faint swirl in the cosmic static. The journey has been dramatic, with an initial announcement of a discovery that was later found to be contaminated by cosmic dust from our own galaxy. This only highlights the immense difficulty of the task, separating an infinitesimal primordial signal from local interference. The quest continues with even more sensitive instruments like the Future Light Bird mission, which will scan the entire sky from space. If it succeeds, it will not just confirm inflation, it will tell us the energy scale at which it occurred, revealing the true strength of the force that built our universe. This is not just a measurement, it is an attempt to listen to the faintest echo of creation, a whisper from a time when all of reality was being violently forged. Even as we search the skies for these ancient gravitational waves, we must confront the very reason scientists first proposed cosmic inflation. This is the horizon problem, a deep puzzle about the uniformity of our cosmos. Look in any direction and the universe appears remarkably similar. The distant reaches of space have the same temperature and density to an astonishing degree of precision. Yet, according to the standard Big Bang model without inflation, this makes no sense. Those regions on opposite sides of the sky were never in contact. There simply hasn't been enough time since the beginning of the universe for light or any influence to travel between them and smooth out their differences. It is as if you walked into a vast auditorium and found millions of people all spaced far apart, humming the same note in perfect pitch without ever having spoken to one another. How could such perfect coordination be possible? Cosmic inflation provides an elegant and powerful solution. It proposes that the entire observable universe was once a single, tiny, interconnected patch. This subatomic speck of space was so small that heat and energy could easily mix throughout it, achieving a uniform temperature, just like a well-stirred cup of coffee. Then inflation happened. In that fleeting moment of hyper-expansion, this tiny, homogenized patch was stretched to a size larger than our entire visible cosmos. The regions we now see as being on opposite horizons were once cozy neighbors, able to communicate and equilibrate before being violently ripped apart. The horizon problem is solved, but in its place we are left with a deeper, more fundamental question. What created that perfect, uniform patch in the first place? What process, operating before inflation even began, could have crafted such a perfectly smooth and homogeneous starting point? Inflation explains how that smoothness was preserved and amplified to cosmic scales. But the origin of that initial perfection remains one of its greatest underlying mysteries. That perfect uniformity is written on a cosmic scale, but it is echoed in the very shape of space itself. Our universe appears to be geometrically flat. This is not flat like a sheet of paper, but flat in the sense that parallel laser beams will never cross or diverge as they travel across the cosmos. They stay perfectly parallel over immense distances. This observed flatness is a sign that the universe exists at a critical balance point, a precise density where the expansion energy and the pull of gravity are perfectly matched. The problem is that this perfect balance is incredibly fragile. Any tiny deviation from this critical density in the early universe would have been wildly amplified over time. If the density had been even slightly higher, gravity would have quickly won, causing the entire cosmos to collapse back in a big crunch after only a few moments. If the density had been slightly lower, the universe would have expanded so rapidly that galaxies and stars could never have formed. For our universe to be as old and as structured as it is, its initial density had to be fine-tuned to an astonishing precision, like balancing a pencil on its tip for billions of years. This is the flatness problem, and it points to a level of cosmic fine-tuning that seems almost miraculous. Cosmic inflation provides a powerful and elegant solution. Think of the universe before inflation as a small, wrinkled sphere, perhaps with significant curvature. The hyper-expansion of inflation acts like a cosmic iron, stretching that sphere to an unimaginable size. Just as the surface of a balloon appears flatter and flatter as you inflate it, any initial curvature in the universe was stretched away until it became negligible on the scales we can observe. Inflation naturally drives the cosmos toward that critical, flat density, explaining the perfection we see without needing a miraculous starting condition. Yet this solution, for all its power, carries its own deep mystery. It tells us that our observable universe is flat, but it also implies that the entire cosmos is likely vastly larger than what we can see. The part we inhabit is just one tiny, smoothed-out patch in a greater whole whose true geometry and size remain forever hidden from us. We are left to wonder, did inflation simply explain away one fine-tuning problem, only to introduce a cosmos of unimaginable and perhaps untestable vastness? That same cosmic flatness we observe on the grandest scale holds the blueprint for everything we see closer to home. The vast cosmic web of galaxies, with its glittering clusters and immense dark voids, did not emerge from a perfectly smooth beginning. Its origin lies in the most microscopic of imperfections, quantum fluctuations imprinted during the inflationary frenzy. In the seething energy of the inflaton field, empty space was not truly empty. It was a turbulent sea of virtual particles, constantly popping in and out of existence due to the inherent uncertainty of quantum mechanics. These were fleeting, microscopic ripples in the field's energy. As the universe underwent its violent exponential expansion, these tiny quantum jitters were caught in the stretch. Imagine a tiny wrinkle on the surface of a balloon. As you inflate the balloon to an enormous size, that tiny wrinkle is magnified into a vast continent-scale crease. Inflation did exactly this, but on a cosmic scale. Those subatomic ripples in the inflaton field were frozen into the fabric of space-time and blown up to astronomical proportions. They became slight variations in density, regions where there was just a little more mass or a little less than the average. These are the primordial seeds, the gravitational anchors for all future structure. After inflation ended and the universe reheated, gravity got to work. Over hundreds of millions of years, it patiently pulled matter toward these slightly denser spots. The extra gravity of a dense region attracted more matter, which made it even denser and increased its gravitational pull in a powerful feedback loop. What began as a minuscule quantum whisper grew into a vast cloud of hydrogen gas, then collapsed into the first stars and galaxies. Those initial seeds stretched across the sky, dictated the entire architecture of the cosmos. The grand filaments of the cosmic web, the dense nodes where galaxy clusters collide, and the immense empty voids between them all trace their lineage back to those random quantum tremors. This is perhaps the most profound connection in all of physics, a direct link between the uncertain, probabilistic world of the ultra-small and the majestic, structured universe of the ultra-large. It means that every galaxy, every star, and our very own solar system ultimately exists because of a random quantum fluctuation in the first moment of time. Our cosmic home was born from a microscopic seed chosen by chance and nurtured by the violent growth of inflation. These quantum seeds planted the cosmic web, but they also helped solve a ghost hunt for a particle that should be everywhere, yet is nowhere to be found. This is the mystery of the magnetic monopole. According to our best theories that unite the fundamental forces of nature, the early universe should have been a factory for these exotic objects. A magnetic monopole is a hypothetical particle that carries a solitary magnetic charge, a north pole without a south, or vice versa. Unlike every magnet we have ever seen, which always comes with two inseparable poles, a monopole would be a fundamental magnetic particle. Grand unified theories suggest these entities should have been created in profusion when the universe was searingly hot and the forces were merged into one. They would be incredibly heavy, potentially as massive as a bacterium, which is astronomical for a single particle. The puzzle is that if they were created, they should be stable, virtually indestructible, and should still be around today, saturating space. We should be tripping over them, yet despite decades of searching, not a single confirmed magnetic monopole has ever been detected. So where did they all go? Cosmic inflation provides a brilliantly simple answer. It swept our cosmic neighborhood clean. Think of the monopoles as a dense crowd of people filling a tiny room. Inflation is like suddenly expanding that room to the size of the entire Earth. The people are still there, but they are now so impossibly far apart that the chance of ever finding another person in your entire life becomes virtually zero. The frantic stretching of space during that inflationary growth spurt diluted the density of these primordial relics to such an extreme degree that they effectively vanished from our observable universe. The monopole problem was, in fact, one of the original motivations for proposing inflation. It elegantly removes a troubling contradiction between theory and observation, but in doing so, it pushes the existence of these fascinating particles to a realm we may never be able to access, far beyond our cosmic horizon. These quantum seeds born from uncertainty lead us to a deeper layer of the mystery. The very process that created them may have depended on physics we simply do not understand. This is the trans-Planckian problem, a profound challenge at the heart of inflation itself. To create the cosmic structures we see today, inflation had to stretch incredibly tiny quantum fluctuations to an astronomical size. But just how tiny were they at the start? The calculations suggest they originated on scales far, far smaller than the Planck length. This is not just a small distance, it is the absolute smallest distance that has any physical meaning in our current understanding of physics. The Planck length is the scale where the fabric of spacetime is thought to become a seething quantum foam, where gravity and quantum mechanics collide and our known laws of physics completely break down. It is the ultimate frontier. The problem is stark. If inflation truly pulled these fluctuations from a realm smaller than this fundamental limit, then the entire beautiful story of structure formation rests on a foundation we cannot describe. It is like trying to predict the exact pattern of a vast, continent-spanning forest by studying the molecular structure of a single seed. The seed itself exists in a domain of chemistry and biology we have not yet discovered. Our predictions for the cosmic microwave background and the distribution of galaxies would then depend critically on assumptions about this unknown physics. How can we trust the outcome if we do not understand the initial conditions? Some physicists see this as a fatal flaw, suggesting that inflation's success might be a lucky coincidence. Others are exploring fascinating solutions, such as modified dispersion relations. This complex term simply means that the relationship between energy and wavelength for particles might have been different in the ultra-high-energy environment of the early universe. Think of it as the rules of sound changing in an exotic material. In normal air, a high-pitched sound wave has a certain energy, but in this primordial medium, that same wave might have carried far less energy, effectively preventing it from probing those impossibly small trans-Planckian distances. This modification could act as a cosmic cushion, protecting the fluctuations from the chaotic physics of the quantum gravity realm and preserving the predictions we so successfully observe. The trans-Planckian problem forces us to confront the limits of our knowledge, reminding us that our cosmic origin story remains incomplete until we can unite the world of the very large with the world of the very small. These quantum seeds, born from a realm beyond our physics, force us to ask an even more fundamental question. What was the universe like before its great growth spurt began? For inflation to start its work and solve the horizon and flatness problems, it seems to have required its own set of perfect initial conditions. The inflaton field needed to be energized and dominant. The patch of space that would become our universe likely needed to be already expanding, and it probably had to be reasonably smooth and flat to begin with. If the pre-inflation universe was a chaotic, crumpled mess, how did a large, uniform region of the inflaton field ever form? This is the initial conditions problem, a puzzle that asks whether inflation truly explains the beginning or merely assumes a very special one. Think of it like trying to start a car. Inflation is the powerful engine that can drive the cosmos to its current state, but someone still had to turn the key. What prepared the universe for that ignition? Some theories suggest that before the hot Big Bang and before inflation, there was a period of cosmic contraction. A previous universe might have collapsed in a big crunch, only to bounce back in a big bang, with the energy of the collapse naturally creating the smooth, expanding, high-energy state needed for inflation to begin. This cyclic or bounce model offers an elegant way to set the stage. Yet this idea, while compelling, simply pushes the ultimate question of beginnings one step further back. What started the cycle? Was there a first bounce, or has the cosmos been cycling for eternity? Other ideas propose that the initial conditions were not special at all, but that any random, chaotic state will, through a quirk of physics, inevitably spawn tiny pockets where inflation can take hold. In this view, our entire cosmos is just one such lucky bubble in a vast, mostly disordered multiverse. The initial conditions problem reminds us that every solution uncovers a deeper layer of mystery. Inflation explains so much about our universe, but it may have simply traded one set of initial mysteries for another, leaving us to wonder if the ultimate beginning will ever be within our grasp. If our cosmos is truly just one bubble in an infinite multiverse, then we face a mathematical paradox so deep it threatens our ability to make any predictions at all. This is the measure problem, a fundamental issue that arises when you try to apply probability to an infinite, eternally inflating reality. In an endless multiverse, every possible event that can happen does happen. Not just once, but an infinite number of times. There are infinite universes where you are reading this script and infinite universes where you are not. Infinite realms where the laws of physics allow for life and infinite realms where they do not. When everything happens infinitely, the concept of probability seems to break down completely. How can you say one outcome is more likely than another if they all occur an unlimited number of times? For scientists, this is not just a philosophical puzzle, it is a crisis. The entire power of a theory like eternal inflation rests on its ability to make predictions, to tell us why our universe has the specific properties we observe. If the theory predicts that all possible values for, say, the strength of dark energy are equally represented across the multiverse, then it explains nothing about why we find ourselves in a universe with a particular value. We need a way to count the bubbles, to find a measure, a mathematical rule that cuts the infinite down to a finite proportion so we can say some outcomes are more common than others. The trouble is, there is no single, obvious way to do this. Different ways of counting lead to wildly different and often absurd conclusions. One approach might be to simply count the number of bubble universes of each type. But since both the number of life-friendly bubbles and the number of lifeless bubbles are infinite, you end up with a meaningless ratio of infinity divided by infinity. Another proposal is to consider a finite slice of time within the multiverse, counting only the bubbles that have formed up to a certain point. But the answer you get can depend entirely on how you choose that time slice, a completely arbitrary decision. Some methods even lead to the baffling youngness paradox. where they predict that the vast majority of observers should exist in universes that have only just formed, still searingly hot from their creation, which is clearly not our situation. Each proposed solution to the measure problem comes with its own set of bizarre consequences and fierce critics. This is more than a technical debate. It strikes at the very heart of whether a multiverse theory can ever be considered scientific. If we cannot find a unique, logical way to calculate probabilities, then the idea that our universe is just one among many may be an untestable and ultimately unscientific proposition. It forces us to ask a profound question: can a theory that describes everything actually explain anything? This staggering fine-tuning of the vacuum energy connects directly back to the engine of inflation itself. We are faced with a numerical chasm so vast it is almost impossible to comprehend: the cosmological constant problem. The same type of energy that powered the inflaton field, the energy of empty space, should still be with us today. Quantum physics tells us that the vacuum is not truly empty, but a seething foam of virtual particles flickering in and out of existence. When we calculate the total energy this quantum frenzy should contribute to the cosmos, the number is astronomically large. Yet, our observations of the universe's expansion show that the actual energy of space, what we call dark energy, is incredibly small. The theoretical prediction and the observed reality are separated by a factor of 1 followed by 120 zeros. This is not just a small error, it is the worst prediction in the entire history of physics. To grasp this discrepancy, imagine calculating the theoretical weight of the entire observable universe, all the galaxies and dark matter, and then stepping on a scale and finding you weigh less than a single feather. The difference is that extreme. The puzzle deepens when we connect it to inflation. The inflaton field's false vacuum energy was immense, driving that frantic hyper-expansion. For the hot Big Bang to begin, that energy had to be dumped, transferred into particles during reheating. But what happened to the underlying, permanent energy of the vacuum itself? Why did it plummet from that incredible high to the whisper we observe today? And why is that whisper not zero? If it were even slightly larger, the universe would have ripped itself apart before stars could form. If it were negative, the cosmos would have collapsed long ago. This is not just a problem of one number, it is a crisis for fundamental physics. It suggests we are profoundly misunderstanding the nature of empty space, or that some exquisite, unknown cancellation mechanism is at work, perfectly balancing the books to 1 part in 10 to the 120th power. Some theorists look to the multiverse for an answer, suggesting that in the vast landscape of bubbles, only those with a cosmological constant as tiny as ours can ever host life. Others seek a new, deeper principle, a law of nature that dynamically sets the energy of nothingness to zero, with dark energy being a faint residual echo. The cosmological constant problem stands as a silent, monumental challenge, a reminder that the greatest mysteries are not always in the distant past, but etched into the very void between the stars. The same quantum uncertainty that seeded our universe may have erased part of its own history. We now face a mystery that echoes one of the most profound puzzles in modern physics, the information paradox. In the world of quantum mechanics, information is never truly lost. The specific details of every particle, its spin, its energy, its quantum state are all preserved. Even if you burn a book to ashes, in principle, the information within it still exists, scrambled into the smoke and heat. This is a foundational rule. Yet, during the frantic expansion of cosmic inflation, something troubling seems to have happened. As space stretched faster than light, vast regions were pushed far beyond our observable horizon. The galaxies, stars, and quantum states that might have existed in those domains are now forever inaccessible to us. The question is, was the information about what existed in those regions simply erased from our causal patch of the universe? If so, does this violate the sacred principle of quantum unitarity, the rule that information must be conserved? This is the information paradox of inflation. One compelling resolution suggests that the information is not lost at all, just hopelessly scrambled and diluted. Think of it like pouring a drop of ink into the ocean. The ink molecules are still there, but they are spread across such a vast volume that recovering the original drop is practically impossible. Similarly, the information from beyond our horizon may still exist in the wider cosmos, but its signal is so faint and spread across such immensities that it is forever beyond our recovery. Another, more radical idea comes from the holographic principle, which proposes that all the information describing a volume of space can actually be encoded on its two-dimensional boundary, like a cosmic DVD. In this view, the information about those lost regions might be stored on our cosmic horizon, a faint, holographic record of everything that inflation carried away. Yet, if information can be stretched beyond reach, what does that say about the ultimate fate of our own cosmic neighborhood? As the acceleration of our universe continues, distant galaxies will one day vanish from our sky, their light too redshifted to ever see again. Will the information they contain be lost to us, just as it was during inflation? This paradox forces us to question the very nature of reality and whether the fundamental laws of physics can survive the most extreme cosmic events. The same quantum uncertainty that may have erased information also points toward a cosmos of unimaginable variety, a concept that finds its most elaborate expression in string theory. This ambitious framework attempts to describe all particles and forces as tiny, vibrating strings. The way a string vibrates determines whether it becomes an electron, a quark, or a photon. But for the math to work, string theory requires more than the three spatial dimensions we experience. It needs extra dimensions, perhaps 6 or 7 of them, all curled up into shapes so small we never notice them. The properties of these shapes, a process called compactification, dictate the laws of physics in our universe. The specific geometry of these hidden dimensions determines the number of particle types, the strength of forces like gravity, and even the value of the cosmological constant. And here is where the landscape emerges. Mathematicians have discovered that there is not just one way to curl up these extra dimensions, but a staggering number. The estimates are beyond astronomical, perhaps 10 to the 500 different possible configurations. Each unique shape corresponds to a different set of physical laws, a different possible vacuum state for a universe. This is the string theory landscape, a vast, abstract terrain of possibilities. Now connect this to eternal inflation. As the inflaton field eternally bubbles, each new pocket universe that forms could be born with a random, different configuration of those extra dimensions. Our universe, with its 4 fundamental forces and its specific particle masses, would simply be one bubble where the compactification happened to produce laws compatible with life. In another bubble, the tight curl of dimensions might result in a universe where electromagnetism is 1 billion times stronger, instantly tearing atoms apart. In another, gravity might be so weak that matter never clumps into galaxies. The string theory landscape provides a physical, though highly theoretical, mechanism for the multiverse. It transforms the abstract idea of eternal inflation into a concrete, if unobservable, process where the fundamental constants of nature are set by a random roll of the cosmic dice within an inconceivably vast landscape of mathematical potential. This idea offers a potential explanation for the baffling fine-tuning we see, but at a profound cost. If every possible universe exists, then the quest for a single, unique theory of everything seems to fade away, replaced by a cosmic lottery where we just happen to draw the winning ticket. Our universe appears incredibly uniform, but a closer look reveals subtle, cosmic fingerprints of imperfection. The cosmic microwave background, that ancient afterglow of the Big Bang, is not perfectly smooth. It is imprinted with tiny variations in temperature, a mottled pattern of hot and cold spots that represent the seeds of future galaxies. For the most part, this pattern follows a specific statistical rule known as Gaussian statistics. This means the fluctuations are essentially random and balanced, like the gentle, rolling hills of a vast landscape. But what if the hills are not entirely random? What if, hidden within this map of the infant cosmos, there are strange, unexpected features that break this statistical rule? This is the puzzle of anisotropy and non-Gaussianity. Anisotropy simply means that the universe is not the same in every direction, and we already see this in the overall temperature differences. But the deeper mystery lies in specific, unusual patterns that some scientists believe they have detected. Imagine looking at a vast field of grass. From a distance, it looks uniformly green and textured. But as you get closer, you notice a few patches where the blades are twisted into strange, intricate knots, or where the color shifts in a way that seems deliberately arranged. These are the potential non-Gaussian signals. They are subtle deviations from the expected randomness, hints of a more complex story written into the first moments of time. What could have caused these statistical anomalies? One compelling possibility is that the inflaton field, the engine of inflation, was not a simple, single entity. Perhaps it was a more complex system with multiple fields interacting and creating intricate interference patterns in the fabric of space-time. Think of it like dropping not one but several pebbles into a still pond. The ripples would cross and overlap, creating a more complex, less purely random pattern on the water's surface. Another, even more mind-bending idea is that these anomalies are cosmic scars, evidence of structures that existed before inflation began. If our universe was born from a chaotic, pre-existing state, the imprint of that ancient turmoil might have been stretched to cosmic proportions, leaving faint statistical echoes in the CMB. The most dramatic proposal suggests these features could be a bruise, the result of a collision with another bubble universe in the vast multiverse. In this scenario, our cosmic bubble was gently bumped by a neighboring one during its early expansion, a contact that left a permanent, asymmetric mark on our sky. While the evidence for these anomalies is still tentative and hotly debated, their potential implications are staggering. They suggest that the story of our cosmic dawn may be far richer and more complicated than the simplest models of inflation can describe. The search for these subtle statistical whispers continues, pushing our telescopes to their limits as we try to read the hidden chapters of our universe's first fleeting moments. Those subtle fingerprints in the cosmic background radiation are not quantum whispers anymore. They are the solid, classical seeds of galaxies. This transformation from the probabilistic quantum world to the definite classical one is a mystery in its own right. How did the ghostly quantum fluctuations of the inflaton field become the concrete, classical density variations we map in the ancient light of the CMB? In the quantum realm, particles exist in a haze of possibilities, a superposition of many states at once. An electron is not in one place, it has a probability of being in many places. The fluctuations during inflation were born from this same uncertainty, mere probabilities rippling through the field. Yet, the temperature variations we observe today are not probabilities, they are fixed, definite measurements. Somewhere on the journey from that fleeting moment to the release of the cosmic microwave background, a fundamental shift occurred. The quantum possibilities had to crystallize into classical reality. Physicists call this the quantum to classical transition, and it is one of the deepest puzzles in all of physics. The leading explanation involves a process known as decoherence. Think of the quantum fluctuation as a delicate, isolated note from a single violin, pure and full of potential. As the universe expanded violently, this note was joined by an immense, roaring orchestra of other fields and particles created during reheating. This environment, this cosmic noise, effectively measures the quantum system, causing it to lose its quantum coherence. The multiple possibilities collapse into a single, recorded outcome, much like a conversation becomes impossible to follow in a crowded, noisy room. The quantum information doesn't vanish, it leaks out and becomes entangled with the environment, making the original fluctuation appear classical to any local observer. But does this fully solve the puzzle? Decoherence explains why we see a definite outcome, but it does not entirely resolve the philosophical unease about what actually selects one specific reality from the menu of possibilities. Why did this particular pattern of hot and cold spots get frozen into our sky and not a slightly different one? The sheer scale of inflation itself may provide a clue. As those tiny quantum ripples were stretched across the cosmos, they were magnified from the subatomic to the astronomical. This process may have acted like a cosmic amplifier, so powerfully enlarging the fluctuations that their quantum fuzziness became irrelevant on the large scales we observe. They were effectively promoted from quantum possibilities to classical facts by the sheer act of cosmic expansion. This transition is not just a footnote in cosmology, it is the very moment our structured universe was born from a sea of potential. It forces us to confront a fundamental question: is the classical world we perceive simply a persistent illusion, a temporary agreement forged in the fiery dawn of time, destined to dissolve back into quantum potential when the last star burns out? That very same cosmic amplification of quantum seeds may have also generated the universe's most elusive component. The story of inflation and the origin of dark matter are deeply intertwined, two cosmic puzzles potentially born from the same primordial fire. We know dark matter exists because its immense gravitational pull guides the rotation of galaxies and bends the path of light itself, yet it remains completely invisible, refusing to interact with ordinary light or matter. Where did this shadowy substance come from, and could its birth certificate have been signed during the inflationary epoch? One compelling idea is that dark matter is a relic particle, a frozen remnant from the universe's violent transition out of inflation. As the inflaton field rolled down its energy hill and unleashed the firestorm of reheating, it did not just produce the quarks and electrons we are made of. It could have also manufactured vast quantities of entirely new, stable particles that simply stopped interacting with the normal cosmic soup almost immediately. These particles would have been left behind as cosmic fossils, their collective gravity silently shaping the universe ever since. The leading candidate for this role is known as a WIMP, a weakly interacting massive particle. The concept is beautifully elegant. In the hot, dense early universe, these particles would have been created and collided with ordinary matter frequently. But as the cosmos expanded and cooled, they would have suddenly frozen out, becoming too sparse to find each other anymore, leaving a permanent relic density that perfectly matches the amount of dark matter we observe today. It is a solution that ties the invisible world of particle physics directly to the grand scale of cosmology. Another, even more fascinating candidate is the action. Unlike a heavy WIMP, the action is predicted to be incredibly light, a billionth or even a trillionth the mass of an electron. Its origin story is directly linked to the kind of fields that drive inflation. Actions are thought to arise from the breaking of a fundamental symmetry in nature, and their field could have been set into motion by the same violent dynamics that powered the inflaton. As this action field oscillated, it could have effectively condensed into a cold, invisible Bose-Einstein condensate permeating all of space, a ghostly quantum wave on a cosmic scale. The properties of these particles are not arbitrary. They are intimately connected to the energy scale of inflation itself. If we could one day measure the mass of the dark matter particle, we could work backwards to calculate the temperature of the universe during reheating, and from there deduce the incredible energy that fueled the inflationary expansion. The search for dark matter is, in a very real sense, a search for the echo of inflation's final moments. Every experiment buried deep underground, hoping to catch the faint bump of a WIMP, and every sophisticated telescope searching for the subtle ways actions might bend light, is not just hunting for a hidden particle. It is an attempt to read a missing page from our universe's very first chapter, a page written in the aftermath of its most dramatic growth spurt. This cosmic preference for matter is perhaps the most personal mystery on our list. Every single thing you see, from the screen in front of you to your own hands, exists only because in the earliest moments, the universe developed a profound and inexplicable bias. For every particle of matter that was created, an equal particle of antimatter should have sprung into existence. Matter and antimatter are perfect counterparts, destined to annihilate each other in a flash of pure energy upon contact. If the cosmos had been perfectly symmetrical, all of the particles forged in the hot Big Bang should have met their antimatter twins and vanished, leaving behind a universe containing nothing but a fading bath of light. Yet here we are, in a cosmos filled with planets, stars, and galaxies made of matter. So where did all the antimatter go? The answer must lie in a fundamental broken symmetry, a slight cosmic cheat that happened during or just after inflation. This process, known as baryogenesis, is the story of how a tiny, 1 in a billion excess of matter particles over antimatter particles was generated and then preserved. The frantic energy of the inflationary era and the subsequent chaos of reheating provided the perfect crucible for this to occur. For baryogenesis to work, 3 conditions known as the Sakharov conditions had to be met. The universe needed to be out of thermal equilibrium, a state of violent, disruptive change rather than a placid, balanced soup. It needed processes that violated a symmetry known as CP symmetry, which essentially means that the laws of physics must treat particles and their antimatter mirror images slightly differently. And it needed interactions that did not conserve baryon number, meaning the total count of matter particles could change. The end of inflation delivered all 3. Reheating was the ultimate departure from equilibrium, a sudden, violent dumping of energy that shook the cosmos to its core. Within that storm, hypothetical, ultra-heavy particles may have decayed. If these decays subtly favored producing matter over antimatter, violating CP symmetry, they could have sown the seeds of the imbalance. One of the most elegant mechanisms is leptogenesis, where this asymmetry is first created in the ghostly realm of neutrinos. In this scenario, heavy, sterile neutrinos decayed asymmetrically, creating a slight excess of ordinary matter particles over antimatter. Through a subtle interplay of forces, this lepton asymmetry was then converted into the baryon asymmetry we live with today. The incredible violence of reheating provided the heat and energy to produce these heavy particles in abundance, while the rapid expansion of the universe ensured that the newly created matter excess was not immediately annihilated back into symmetry. The result was a universe that, for every 10 billion particles of antimatter, contained 10 billion and 1 particles of matter. The subsequent annihilation wiped the slate almost clean, leaving behind that 1 in 10 billion residue. And that residue, that tiny, fragile surplus, is everything. It is every atom in your body, every star in the night sky, every structure we call home. The entire visible universe is built from the ashes of that near-perfect annihilation, a monument to a broken symmetry written into the laws of physics during the universe's most transformative second. That delicate matter-antimatter asymmetry, a 1 in 10 billion miracle, was then woven into the very fabric of the cosmos by the gravitational pull of the universe's first structures. But the story of those structures holds a peculiar detail, a ghostly signature of inflation that defies our everyday intuition about cause and effect. The cosmic microwave background reveals a startling coordination. Vast patches of the sky, separated by distances so immense that light has not had time to travel between them since the beginning of the universe, display almost identical patterns of hot and cold. These are the super-horizon fluctuations, correlations that stretch across scales larger than our cosmic horizon. How can 2 regions that have never been in contact, never exchanged a single photon or any form of information, know to wear the same temperature? This is not a minor curiosity, it is a profound prediction of cosmic inflation and one of its most powerful pieces of evidence. The solution lies in their shared past. Today, these two distant points are strangers, living in isolated cosmic provinces with no communication. But in the fleeting instant before inflation began, the entire observable universe was a single, minuscule, interconnected dot. Those 2 points were once intimate neighbors, closer together than 2 atoms in a grain of sand. They were able to talk, to equilibrate, to synchronize their properties in that tiny, primordial realm. Then inflation acted like a cosmic zoom lens, violently stretching that tiny, coordinated patch to a size far greater than our current horizon. The connection was not broken by distance, it was frozen in place by the expansion, a fossilized handshake from a time when the entire cosmos was small enough for a conversation to happen. This is a crucial test that separates inflation from most other theories of the early universe. Without a period of rapid, faster-than-light expansion, there is simply no mechanism to create these vast, coordinated patterns. Alternative models might create fluctuations, but they would only be local, limited to scales within the cosmic horizon where light could have traveled. The undeniable presence of these super-horizon correlations in the CMB is like finding 2 identical, intricate snowflakes on opposite sides of a continent. It tells us they must have formed together in the same cloud before being carried apart by impossible winds. This ghostly coordination, this fossil of a time when everything was connected, stands as one of the most compelling and enduring relics from the universe's first and most dramatic growth spurt. While inflation's predictions are compelling, it is far from the only story told about our cosmic dawn. Other theories challenge its dominance, offering radically different visions of the very beginning. One of the most profound is the cyclic model, a universe without a true start. In this vision, our cosmos undergoes an endless series of cycles. Each begins with a period of slow, gentle expansion, much like what we see today, allowing galaxies and life to form. But this era is followed by a great contraction, a big crunch where all matter and energy are drawn back together. Instead of collapsing into a singularity, the universe rebounds in a big bounce powered by new physics, and a new cycle of expansion begins. This model elegantly explains the uniformity and flatness of our universe through the relentless grinding of these cycles. Just as repeatedly stretching and folding dough makes it smooth and flat, each bounce irons out wrinkles and dilutes any curvature, naturally creating the conditions we observe without needing a singular, explosive inflation. Another path is string gas cosmology, which emerges from the world of string theory. Here, the early universe was a hot, dense tangle of the fundamental strings from which all particles are made. This primordial gas of strings existed in a compact, 9-dimensional space. As 3 of those dimensions expanded, becoming the vast universe we see, the other 6 curled up into the tiny shapes that determine our laws of physics. In this model, the uniformity of the cosmos arises not from a rapid expansion, but from thermal equilibrium. The strings were constantly interacting and exchanging energy, reaching a uniform temperature throughout their tightly packed space, much like a room that settles into a single, even warmth. When the 3 dimensions we inhabit then expanded, that thermal smoothness was simply inherited and stretched across the sky. So how can we possibly choose between these competing visions of creation? The key lies in their unique observational fingerprints. While inflation predicts a specific, nearly scale invariant pattern of primordial fluctuations, the alternatives leave different marks. The cyclic model, for instance, might produce a telltale signature in the gravitational wave background. The collision of the cosmic membranes or branes that trigger each new cycle could generate a spectrum of waves distinct from those of inflation. String gas cosmology makes a very specific prediction about the oldest light in the universe. It suggests that the temperature fluctuations in the cosmic microwave background should not be the same on all scales. Instead, it predicts a turnover, a specific scale where the pattern of hot and cold spots changes character in a way that inflation would not produce. Finding this subtle shift in the data would be a powerful clue pointing away from inflation and toward a stringy origin. The search for these signals is more than a technical debate, it is a struggle for the soul of cosmology. Are we living in a unique, inflated universe or one of countless cycles in an eternal cosmic heartbeat? Did our smooth cosmos emerge from a frantic, quantum-driven stretch or from the calm, thermal death of a previous epoch? Each theory tells a grand, beautiful story, but only one can be true. The answer is written in the faint patterns of the ancient sky, waiting for our next generation of telescopes to read it. The shape of the inflaton field's potential energy was not arbitrary. It was a precise cosmic blueprint. For our universe to emerge with its vast, flat, and structured nature, the hill the field rolled down had to be incredibly shallow and smooth. This is the mystery of fine-tuning in the inflationary potential. If the slope had been even slightly steeper, the field would have rolled down too quickly, ending inflation before it could solve the horizon and flatness problems. The universe would have remained a small, lumpy, and curved space, utterly unrecognizable. Conversely, if the slope had been too flat, the field might have gotten stuck, leading to eternal inflation in our entire region and preventing the hot Big Bang from ever igniting here. The required flatness is so extreme it defies simple chance. It is like balancing a marble on the rim of a vast, continent-spanning bowl, a delicate equilibrium that had to persist for that critical fraction of a second. This puzzle becomes even more acute when we try to embed inflation into our best theories of quantum gravity, such as supergravity. Here we encounter the eta problem. In supergravity, new terms naturally appear in the equations that want to steepen the inflaton's potential. These corrections are typically large, making the slope far too sharp for successful inflation to occur. To achieve the necessary flatness, an exquisite and seemingly unnatural cancellation must happen, where these steepening effects are almost perfectly balanced by other factors. Why would the universe's fundamental laws conspire in such a precise way? This profound fine-tuning forces us to consider two radical possibilities. The first is that a deeper, undiscovered principle of nature protects the flatness of the potential, a symmetry or mechanism we have not yet identified that naturally enforces the shallow slope required for a cosmos like ours to exist. The second, more Copernican possibility is that there is no deeper principle, only a brutal selection effect. In a vast multiverse, every possible shape for the inflationary potential is realized in some bubble universe. In the overwhelming majority, the slope is too steep or too flat, and those universes remain sterile, empty, or short-lived. Only in the rare bubbles like ours, where a cosmic lottery produced the just right conditions, can galaxies, stars, and observers ever arise to ask the question. The fine-tuning of the inflaton potential may not be a puzzle to be solved, but a simple statement of fact. We can only exist in a universe that allowed for our existence. The fine-tuning of the inflaton field pushes our inquiry to the very edge of time itself. What reality could have possibly set the stage for such a delicate cosmic trigger? The possibility of a pre-inflationary universe forces us to confront the ultimate blank slate, an epoch whose every trace was likely erased by the subsequent storm of expansion. Yet theorists dare to imagine what might have been. One vision paints a picture of a chaotic quantum foam. At scales a trillion times smaller than an atom, the fabric of space-time would not have been smooth and continuous. It would have been a turbulent, frothing sea, with tiny wormholes and baby universes constantly bubbling up and dissolving back into the energetic vacuum. In this frenzied, probabilistic realm, our entire cosmos could have been just one particularly successful bubble, a random fluctuation that, against all odds, caught the inflationary fire and blossomed into everything we know. A second, profoundly different idea is the cosmic cycle. Perhaps our universe is not the first, but merely the latest in an endless series. A previous cosmos may have expanded to a great size, then reversed its course in a great contraction, collapsing inward in a big crunch. But instead of ending in a singularity, new physics, perhaps from string theory, could have caused it to bounce. The energy of that collapse would have been recycled, reborn in a new Big Bang and a new period of inflation. In this view, the smooth, flat, uniform conditions inflation needs to start are not a mystery. They are the natural result of the endless grinding of these cycles, like waves smoothing pebbles on a shore over eons. A third, more serene possibility is that it all began in a static, eternal state. A universe that simply was and always had been, until some random quantum event destabilized a patch of space, tipping it into the inflationary cascade that led to our reality. The central, haunting question is whether any scar, any fingerprint from this pre-inflationary era could have possibly survived. The violent stretching of inflation acted like a cosmic reset button, smoothing and diluting any prior features to near invisibility. Yet, like a ghost image on an old television screen, the most profound anomalies might still linger. Some scientists search for strange, non-Gaussian patterns in the cosmic microwave background, statistical oddities that deviate from the predictions of simple inflation. These could be the cosmic bruises from a collision with another universe in the pre-inflationary foam, or the faint, stretched echo of a structure that existed before time as we know it began. The search for these signals is a gamble on the resilience of information, a hope that the universe in its first violent act did not perfectly erase its own origin story. The same force that birthed our universe may one day be its end. This eerie connection links the furious expansion of the cosmic dawn to the quiet, relentless acceleration we see today. The dark energy currently pushing galaxies apart behaves like a faint, ghostly echo of the inflaton field that once drove inflation. Both are forms of vacuum energy, a fundamental pressure inherent to empty space itself. The critical difference is one of intensity. During inflation, the vacuum energy was unimaginably potent, driving a doubling of cosmic size in fractions of a second. Today, dark energy is incredibly weak, a gentle but persistent push causing a far more gradual acceleration. This raises a profound question. Are we living in the tail end of a single, drawn-out inflationary event? Could our current epoch be a slow-roll version of that primordial frenzy, playing out over billions of years instead of a fleeting instant? The answer to that question dictates the ultimate fate of everything. If dark energy maintains its current gentle push, the future is one of increasing isolation. Galaxies beyond our local group will fade from view, their light stretched beyond detectability, leaving our descendants with a sky devoid of external galaxies, a lonely island in an ever-cooling cosmos. But a more terrifying possibility exists: the Big Rip. This scenario unfolds if the strength of dark energy increases over time. In this future, the repulsive force would eventually overcome every binding force in nature. First, the cosmic web of galaxies would be torn apart. Then, individual galaxies themselves would be shredded. As the acceleration grows, gravity would lose its grip on our own Milky Way, sending stars flying into the void. The final acts would be almost unimaginably violent. Planets would be ripped from their stars. Then, the very planets and stars would be torn asunder, their gravity and chemical bonds failing. In the last moments, atoms themselves would be ripped apart, followed by nuclei, and finally, the fabric of space-time would be shredded. This apocalyptic finale is a direct, if horrifying, mirror of the inflationary epoch. It would be inflation reborn, not as a creative force, but as an agent of total cosmic dissolution. The same physics that once stretched a quantum seed into a universe would, in this scenario, stretch that same universe into nothingness. This cyclical symmetry is both beautiful and terrifying, suggesting that the engine of creation and destruction may be one and the same, a fundamental property of the void whose character determines whether we live in a cosmos of structure and life, or one destined for a final, silent, and empty tier. The same cosmic horizon that defines our entire view of the universe also represents a fundamental wall beyond which we cannot see. This is the ultimate limit of observability, a sobering frontier that may forever keep the deepest truths of cosmic inflation just out of reach. Our entire observable universe is a finite bubble, a sphere defined by the distance light has been able to travel since the Big Bang. Everything we can ever hope to see, from the nearest star to the most distant galaxy, resides within this cosmic horizon. Yet the full, true extent of the cosmos is almost certainly far vaster, a consequence of that frantic inflationary stretch. The majority of the universe was inflated away from us, carried off by the expansion of space itself at speeds greater than light, severing any possible causal connection. We are like a sailor on a vast, dark ocean, able to see only the small circle illuminated by our own lantern, while the true scale of the sea remains an impenetrable mystery. This reality places severe constraints on our quest for confirmation. The most profound theories, like eternal inflation, suggest an endless froth of bubble universes beyond our horizon. But if these other realms are forever disconnected from our own, how can we ever prove they exist? Any direct evidence is, by definition, impossible to obtain. We are left searching for indirect, circumstantial clues within our own tiny patch, like trying to map an entire continent by studying a single grain of sand. The patterns in the cosmic microwave background and the large-scale structure of galaxies offer hints, but they are whispers from a play whose vast majority of acts are performed in a theater we can never enter. This forces a profound philosophical question upon science. Can a theory that describes realities fundamentally beyond our observation ever be truly scientific? The quest to understand our own origin story may ultimately bump against an unbreachable wall, leaving us to wonder if the grandest cosmic truths are destined to remain beautiful, untestable ideas, forever echoing in the dark just beyond the edge of our sight. From the silent trigger that ignited existence to the invisible walls of our cosmic horizon, these 25 mysteries paint a humbling portrait of our quest for understanding. We began with the ultimate question of a first cause, then witnessed the strange physics of the inflaton field and its graceful yet finely tuned exit. We ventured into the bubbling multiverse and hunted for primordial gravitational waves, all to solve fundamental puzzles of our universe's uniformity and shape. We traced the cosmic web back to quantum seeds, confronted missing monopoles, and grappled with the trans-Planckian problem where our very physics breaks down. The journey led us through the maze of the measure problem, the staggering fine-tuning of the cosmological constant, and the potential loss of quantum information. We saw how string theory's landscape offers a dizzying array of possibilities, and how subtle anomalies in the ancient sky might hint at a more complex origin. We witnessed the quantum world becoming classical, explored the intimate link between inflation and the birth of dark matter, and uncovered the fragile asymmetry between matter and antimatter that makes our existence possible. We decoded the ghostly coordination of super-horizon fluctuations and weighed inflation against its rivals, the cyclic universe and string gas cosmology. Finally, we saw how the very mechanism of inflation might be finely tuned itself, pointing to a pre-inflationary era whose secrets are forever erased, and how the same force that created everything could one day tear it all apart in a final big rip. The triumphant theory of cosmic inflation did not provide final answers. Instead, it flung open a Pandora's box, revealing layers of deeper, more profound questions about the fundamental nature of reality, time, and our place within an unimaginable whole. Each mystery is a doorway, and behind it lies not just a solution but another, even more magnificent question. So we turn to you. Which of these cosmic enigmas captures your imagination the most? Is it the ghostly pull of dark matter, the silent emptiness of the void, or the haunting possibility of other universes? Share your thoughts and never stop wondering about the greatest secrets the cosmos has.